Let's continue our discussion on decision trees. This section, we are going to focus on classification trees. So we studied the difference between decision trees and regular regression methods, essentially regression trees versus regression itself, right? Regression, we actually specifically refer to linear regression, nonlinear regression. But here, decision trees refers to regression trees. Meaning that decision tree-based regression. And then we studied tree building and pruning process. And in this section, we want to study classification trees, which is different from regression trees in the sense that we're using categorical variables as the dependent variable. And then after that, we can briefly discuss application of trees. So what are classification trees? They are very similar to regression tree, except that it is used to predict a qualitative response rather than a quantitative response. In other words, a dependent variable would be categorical, would be qualitative rather than numeric. For a classification tree, we predict that each observation belongs to the most commonly occurring class of training observations in the region to which it belongs to. So if you think about the node concept, leaves concept in decision trees, so essentially says if in a specific leaf node, we have more than 85 or 90% of those nodes belong to a specific category, then we predict that node be in that specific category. That's the idea. Just as in the regression setting, we use recursive binary splitting to grow a classification tree. In a classification setting, MSE cannot be used as a criterion for making a binary splits because it's categorical. You are not able to calculate that MSE. The cost function instead is defined as below. It's you can see that the same thing. K is the variable that you decided to split on. Tk is the threshold. And then this objective function or the cost function is a weighted average of the G. Let's think about what is G. G is something called the impurity of the left and right subset. And of course, M left or right is a number of instances in the left or right subset. So that's a weight, that's a G. Let's take a look at what exactly is this G. G itself is defined as this equation 6.1, Gini impurity, Gi equals to 1 minus K from 1 to N Pik squared. So this is also called Gini index or Gini impurity. And then just take a look at what is Pik. Pik is the ratio of class K instances among the training instances in the ith node. So let's think, right, it's for a specific ith node. We want to see what percentage belongs to some sort of classes, some sort of categorical variable. And then that ratio, if you have 3 classes, for example, you have 3 ratios in that node, and then you use that 1 minus those 3 ratios squared to get your Gi. So what happens? It is a measure of total variance across the K classes. The Gini index takes on a small value if all of the PIKs are close to 1. Right, so if this one is close to 1, if all of the PIK is close to 1 or 0, because you have to, some other categories have to be close to 1, some other ones must be close to 0 instead. So 1 minus something close to 1, the rest of them close to 0, so that at the end of the day, the GI should be close to 0 if um, it can be defined into, it can be categorized to a specific category. So for this reason, the Gini index is referred to as a measure of node purity. A small value indicates that a node contains predominantly observations from a single class. As I just mentioned, right, if PIK for a particular category K is close to 1, the rest of them would be close to 0, so that this GI is close to 0. So that's why a small value indicates that a node contains predominantly observations from a single class. That's GI. Now, there's another alternative to the Gini index. So instead of using Gini index, we use something called cross entropy, which is given by the following function, which is hi equal to negative of this summation. So if you look at this PIK, which we already know, that for this node, what percentage goes to specific category K, and times log of this PIK, and then we sum all of the classes K equal to 1 to n, sum all the classes together to summarize the entropy, we call it cross entropy of this node. And then if you use this instead of G into your cost function, that would be an alternative way. And it turns out that Gini index and the cross entropy are very similar metric numerically. So you could use either one of them. Majority of people use Gini index. So this is something you should pay attention. When you use scikit-learn, you should know which metric or which toggle that you can select, or which parameter you can set to choose from a specific index. Okay, so let's use, that's really the classification tree. So if you think about it, the difference between a regression tree versus classification tree is really the difference of the objective function. And then at the end of the day, we're still trying to figure out what would be the best splitted variable and what would be the best threshold that we should use. So let's look at this as an example from Iris dataset. So you load that data of Iris dataset, and then look at only the third and the fourth column. 0, 1 would be the first two, and 2 and 3 would be the third and fourth, right? So you load the third and fourth columns of variables, which happen to be petal length and width. And then our y variable is coming from the Iris data set dot target. And that target has 3 different types of flowers, one of them being setosa, second one is versicolor, and the third one is virginica. So those 3 types of flowers is going to be differentiated by petal length and width. Let's see how we can do it. We use decision tree classifier and max steps equal to 2 to build this tree object, and then we fit tree underscore CLF dot fit the x versus y. Once we do that, it's already have a decision tree model, and we can leverage this export graph viz to look at the class Iris decision tree. And then in this decision tree, let's look at the details of the numbers. So here, if you see, okay, petal length, when petal length is less than or equal to 2.45, that's true, what we can get is the left leaf node. And then on the right hand essentially says, if petal length is larger than 2.45, when that is false, when this one is false, then it's larger than 2.45. You come to the right hand side. And then also let's look at total number of samples. You have 150 samples, 50 of them belongs to the left node, and the other 100 goes to the right node. And then among these 50, originally you have 50 of setosa, 50 of versicolor, and 50 of virginica. And then the Gini index for the whole data set is around 0.667. So what we're trying to do here is trying to find the best split so that our Gini index can decrease the most. The same thing as what we discussed earlier in regression trees. We're trying to find a split to decrease the most of that J function, and that J function in regression trees are related to MSE, but here this function J function is related to the Gini index. Okay, and then you can see that we also have a class here, right? So this class for the second level, you can see the first one on the left-hand side, because it's 100%, 50 of them belongs to setosa. As a result, Gini index becomes 0. 1 minus 1 minus 0 minus 0 is 0. That's why Gini index becomes 0, and then on the right-hand side, the Gini index 0.5. If you continue to split, look at the next level, depths of 2, you apparently find that Gini index is not quite 0 because we have 5 virginica type of flowers blend into this category in this leaf node. And then on the right-hand side, one of the versicolor turns out to be in this category. So that's essentially misclassification, if you recall, right? This can be defined as misclassification. Nevertheless, we're not trying to figure out 100% classification. With misclassification, essentially says if data is complicated with some sort of regularization, as we mentioned earlier, you would do a better job in general for the whole data set. And here you can see using decision tree decision boundaries to represent the same thing. The first level is the first split is really happening here, so that we can separate the first category of flowers, which is setosa, versus the rest. And then for the second part, you could have the left side node. On the left side node, you have 49 versicolor and 5 virginica. It would be this part. You split, and then you still have some sort of it's really here. It's really here, so that you have majority of them. So let's say 50 of among 50 of versicolor and 50 of or 54 of versicolor and 46 of virginica. So the depth 1, depth 0 is essentially, let's go over this one more time. Depth 0 for sure. What you do is depth 1 is you split. Oh, there we go. So first split is based on the petal length, which is less than 2.45 this side versus what's happening on the right-hand side. And then let's look at this one. And then the split is petal width less than or equal to 1.75. So the second, this is really that split. In depth 1, you did this split based on petal width, so that you would be able to differentiate between this part and this part. This part and that part would be this, and that. Of course, if you continue with one more, you would be able to, yes. So that if you look at this chart, essentially, one of them is Virginica, saying that this part is really, the green color is really the rightmost leaf node. And then this purplish color is this node, this green node. So that's the split. Of course, you could continue to split by doing one more split. Here is not related to this example, this particular chart. That's decision tree, decision boundaries. Now, give you more example to see what happens if you have regularization versus you do not have any regularization. If you use minimum sample leaf equal to 4, to see that a leaf node has at least equal to 4 observations, then you could have a decision boundary looking like this. But if you don't have this minimum sample leaf equal to 4, then it turns out to be what's on the left-hand side. And then what's on the left-hand side apparently has an issue that it's trying to fit this particular blue and then try to make the boundary to be very wiggly. It has potential issues of overfitting here, rather than with the regularization. It doesn't have any overfitting problem. So for your understanding, you should play with some of these regularization parameters that we listed in the slides. Let's think about what are the advantages and disadvantages of trees. Trees are very easy to explain to people. In fact, they're even easier to explain than linear regression. So as I just mentioned here, you can see, okay, I have two variables. One of them is petal length, second one is petal width. The first thing what I did was petal length. Using petal length, I would be able to split the data. And then for this particular node, I would be able to use petal width to split the data. Now, if you think about this node, what it means is, starting from the top, says petal length larger than 2.45 and petal width less than 1.75 will result into this node, right? Pay attention, I mentioned that petal length and petal width. That's something called interaction. If you recall, we mentioned if you use decision tree, it does have a good aspect, that is, it can deal with interaction. This particular branch goes through this branch is one interaction between petal length and petal width. If you look at the rightmost branch, it's also interaction. It says petal length larger than 2.5 and petal width larger than 1.75, resulting in this purple color node. That's a good thing. It's easy to explain. And some people believe that decision trees are more easily mirror human decision making than do the regression and classification approaches seen in previous chapters. And trees can be displayed graphically and are easily interpreted even by a non-expert, especially they are small. If the trees are small, it's much easier to be explained. Trees can easily handle qualitative predictors without need to create dummy variables, just categories. Just put them in, and then you would be able to come out with a classification tree. Unfortunately, trees generally do not have the same level of predictive accuracy as some of the other predictions and classification approaches. However, the predictive performance of trees can be substantially improved by aggregating many decision trees. That's something that we're going to discuss next, essentially ensemble methods and random forests. So as a summary, trees are seldom the best models, but they are the simplest to understand. Trees can be easily improved by tuning complexity and considering an ensemble of trees, which would be our discussion of ensemble methods and random forests coming next. Thank you.